Hey, welcome back. So now we're going into 4.7. This will be Kashi Euler equations. It's very similar to what we did in 4.3 with homogeneous linear differential equations with constant coefficients. The big change now will be that the coefficients are not necessarily constant, they're variable. And for the types we look at, they'll have solutions of the form x to the m. So back in 4.3, the form of the solution was always e to the mx. Now the form of the solutions will be x to the m. Okay, so let's kind of dive in and take a look at these guys. We'll sort of form a new characteristic equation based off of this the supposed solution. And from that characteristic equation, we'll have different cases, just like we did before. Unique, distinct real roots, the repeated real roots, and then the complex roots. Okay, it's very, very similar to what we did before, though. Okay, so anyways, let's take a look at kind of just an example of what these things look like. We could take one of the problems directly from the homework. So problem 1. We have, C1, or I didn't know the answer. We have x squared y double prime minus 6y equals 0. Okay, we're going to suppose our solution is of the form x to the m. Okay, so our solution y equals x to the m. And then we're going to get the derivatives of this thing and put it into that differential equation. So y prime is going to be, from the power rule, bring down the m, then you got x to the m minus 1. And then the second derivative, now bring down the m minus 1. So it'll be m times m minus 1, x to the m minus 1 minus 1, which will be m minus 2. Right? Then we're going to plop all this material into the differential equation. So we get x squared times m minus 1 times x to the m minus 2. Then minus 6 times y, which is x to the m. We have two terms with the same base, so you can, because they're being multiplied by each other, we can add the exponents of those two terms. So you'd end up with m times m minus 1 times x to the m minus 2 plus 2, which of course is just x to the m. I forgot to put a 0 on the other side. And then minus 6x to the m, and that will equal 0. Then you can factor out the x to the m, and what you have is kind of a characteristic equation. Okay, so we'll just toss out the x to the m part, toss that in the trash, and work in particular with this object here, which is after I distribute m squared minus m minus 6. That'll equal 0. So my m values, m minus 3, and then m plus 2 equals 0. So that's going to give me two different solutions, x to the 3 and then x to the negative 2. All right, so my m equals 3 gives me the first part of my general solution, c1x cubed. And then when I solve the m plus 2, put it equal to 0, you get m as negative 2, so you get plus c2x to the negative 2. Okay, and that turns out to be the solution, the general solution. Okay, so what you do then in this in the reading is kind of just again go through all the different types. So the first case is distinct roots. So just case 1, distinct roots. And so let's look at another problem in the homework. Maybe this one a little bit more annoying. So number 4. Let me pull this over. I have x squared y double prime minus 3x y prime minus 10y. Well, let's do an even harder one with like higher derivatives than just 2. I think there might have been one of those in here. So there's one. Oh, that's a different kind of solution than what we're used to. Well, here's one then. All right, so I have number 9. Let's take a look at number 9. They have xy, and then the fourth derivative of y plus 6y with the third derivative equals 0. So it looks like I'm going to be able to rewrite this as x times the fourth derivative. So I have the first guy is x to the m, y prime is mx to the m minus 1, y double prime is m times m minus 1, x to the m minus 2, y triple prime will be m times m minus 1 times m minus 2, x to the m minus 3, and then the fourth derivative, giving myself a little more room, m times m minus 1 times m minus 2 times m minus 3, x to the m minus 4. Okay. So plugging that into my differential equation, I'll have x times m minus 1 times m minus 2 times m minus 3, x to the m minus 4, plus 6 times the third derivative, m times m minus 1 times m minus 2, x to the m minus 3. And all of that will equal 0. Okay. Rewriting this a little bit, again, I have that like base scenario, so x times x to the m minus 4. And it's always going to work out so you can factor the x portion out of your expression. Okay, so you would have x times x to the m minus 4 will be x to the m minus 4 plus 1, which is x to the m minus 3. And then you have all this stuff in front of it. Okay, and on the plus, then the 6m times m minus 1 times m minus 2, x to the m minus 3 is 0. You could factor a lot of stuff out, right? There's a common factor of m, there's a common factor of m minus 1, and a common factor of m minus 2, and a common factor of x to the m minus 3. So I factor all that material out. So the x to the m minus 3 here. And then m times m minus 1 times m minus 2, I'm left with m minus 3 from the first part. That's the only thing that's left. And then the second part, I'm left with a 6. Okay. So it'd be m minus 3 plus 6. And that's equal to 0. You can kind of just toss the x to the m minus 3 in the trash. And you're left with m times m minus 1 times m minus 2 times m plus 3 equals 0. And so your kind of roots are m equals 0, 1, 2, and then negative 3. And so our general solution should be y equals c1 x to the 0, which is just 1, plus c2 x to the first, plus c3 x squared, plus c4 x to the negative 3. Okay. So now let's look at case 2. And case 2, this is now when we have repeated roots. And if you remember what we did with repeated roots in what section was that, 4.3? If you had a repeated root, what we did was kind of just sneak in an x, right? So if you had m1 repeated, it'd go c1e to the m1x plus c2x e to the m1x. Okay, it's kind of similar, but instead of an x, we're going to use ln x. Okay, so let me get back to where I was. Okay. So the form, supposing you had m1, or just we'll say call it m repeated, you would have c1 x to the m plus c2 x to the m, and then you're going to tack on an ln x. Okay. Okay, so let's find one of those guys in here somewhere. I guess the second problem looks like one of them. Well, let's do number 6. Okay. So I have x squared y double prime plus 13xy prime plus 36y is 0. I'm going to you know, the form of my solution is y equals x to the m, finding derivatives all the way up to the second derivative, mx to the m minus 1, and then the second derivative, m times m minus 1 x to the m minus 2. Plug that stuff into your differential equation, so you get x squared times m minus 1 times x to the m minus 2 plus 13x times m times x to the m minus 1 plus 36x to the m equals 0. And you see the x squared and the x to the m minus 2 will combine to give you x to the m. Here the x and the x to the m minus 1 will combine to give you x to the m. So all three terms will have a factor of x to the m, which you're going to be able to factor out. Right? So just seeing that, 1 x to the m plus 13 m x to the m plus 36 x to the m is 0. And then you could factor and basically throw out the x to the m portion, and you're left with m times m minus 1 plus 13m plus 36 equals 0. Distributing, I get m squared minus m plus 13m plus 36 equals 0. Combine like terms, so you get m squared plus 12m plus 36 is 0. So you get m plus 6 times m plus 6. So you have a repeated root of negative 6. And so our general solution will be c1 x to the negative 6 plus c2 x to the negative 6 ln x. Okay. So you just tack on an ln x. Case 3 then with conjugate roots. Let's take a look at that thing. So I think this is section 4, case 3, conjugate. Conjugate complex roots. So suppose we have m1 is alpha plus I beta, and m2 is alpha minus I beta. Your solution, your general solution, technically would be y equals c1 x to the alpha plus I beta plus c2 x to the alpha minus I beta. But we want to get rid of that imaginary number. Just like we did before, we're going to rewrite it using Euler's formula. So x to the ib, we can rewrite as e to the ln of x to the ib, which is equal to e to the I beta using the power rule, right? So we could take this I b part, which should be a little beta, and put it in front of the natural log, and we get I beta ln x. And then you could use Euler's formula on it to rewrite it as cosine of beta ln x plus I sine of beta ln x. And then we could take the parts and basically multiply them by any constant we want. And so in general, our solution, y will equal x to the alpha times c1 cosine of beta ln x plus c2 sine of beta ln x. And if you look back at the form for complex roots when we were dealing with the homogeneous linear constant coefficient problems, you kind of have the same form. It's just now you're kind of tacking in an ln of x, and of course on the outside you have an x to the alpha as opposed to e to the alpha x. Okay, so a little comparison contrast there, doesn't hurt. Anyways, let's look at one of these problems. Number 7 looks nasty enough for our purposes, so look at number 7. 3x squared y double prime plus 6xy prime plus y equals 0. And again, hopefully you get to the point where you just remember what the y double prime and the y prime and the y is, so you don't have to derive it every time. But so here it'll give us 3x squared times m minus 1 x to the m minus 2 plus 6x m times x to the m minus 1 plus x to the m. That will equal 0. Factor out the x to the m portion. And of course, again, this times this will give you an x to the m. This times this will give you an x to the m. And you'll just be left with 3m times m minus 1 plus 6m plus 1 equals 0. Ditch the x to the m part, you get 3m squared minus 3m plus 6m plus 1 is 0. So you get 3m squared plus 3m plus 1 is 0. Can't factor it, right? So you go to your quadratic. M is going to be negative b plus or minus the square root of b squared minus 4 times a times c all over 2 times a. So we get negative 1/2 plus or minus 9 minus 12 is negative 3. So you get the square root of negative 3, which is square root 3i all over 6. And those are our roots. So our general solution, y must equal x to the negative 1/2. X to the negative 1/2 times c1 cosine root 3 all over 6 ln x, believe it or not, plus c2 sine root 3 all over 6 ln x. And that would be your answer. You can see there to the right. Okay, so those are the homogeneous versions. After you go through all that material, you look at some initial value problems where you're solving for C1 and C2. Here's a third order problem. We did a fourth order problem, which was more complicated than that. Then you'll start looking at the non-homogeneous equations, and unfortunately you have to do variation of parameters on these. Okay, so I think this is section 5 in my notes. When you have L of y instead of equaling 0, g of x, so non-homogeneous, and sadly enough you have to use variation of parameters. Okay. So sad face. All right. Let's take a look at one of these guys. Let's scroll down a little bit. I guess number 10 maybe. Let's write it down first. xy double prime minus 8y prime equals x to the 8. So what you do is solve the associated homogeneous differential equation to get your y1, y2, and your complementary part of your solution. And then you're going to use variation of parameters to build the particular parts. I'm looking for, there we go. Okay, so I always got my formulas for variation of parameters sitting around. I click those open so I can work through this problem. Okay, so first I'm going to get the complementary solution. It'll be x times m minus 1 times x to the m minus 2 minus 8 times m x to the m minus 1 equals 0. Factor out the x to the m minus 1 this time and throw it away. And then you have just m times m minus 1 minus 8m equals 0. So you have m squared minus m minus 8m equals 0. So you have m squared minus 9m equals 0. Factor out an m, and you get m minus 9 equals 0. So our roots are 0 and 9, and then our complementary part of the solution will be x to the 0, so just 1. So c1 times 1 plus c2 x to the 9th. Okay. Okay. On the right there, you see my formulas for u1 and u2 for variation parameters. I just want to note here that y1 is just 1, and then y2 is the x to the 9th part. Okay. So just kind of put that here in a box. I'm going to need the Wronskian built from those two functions, so I don't know where to carry on here. Let's carry on to the this here. So my Wronskian, taking those two functions, 1 and x to the 9th, would be 0, and then 9x to the 8th. So 1 times 9x to the 8th is 9x to the 8th for my Wronskian. And then I can start building my u1. Okay, so u1 prime is negative y2, so negative x to the 9th, times f of x, which is apparently x to the 8th, all over the Wronskian, which is 9x to the 8th. And let's simplify that. So that works out kind of nice. So I get x to the 9th all over 9. And then integrate both sides. So I get u1 equals negative x to the 10th all over 90. Ugh, that doesn't seem right. Yeah, well. Sort of wondering, did I get my formula wrong? Did I write my formulas down wrong? y2 is x to the 9th. Negative times the x, it's x to the 8th. Yeah. Okay, well, we'll just go with it. So u2 is going to be u2 prime from my formula is going to be y1, which is just 1, times f of x, which is x to the 8th. Well, this thing right here is f of x, by the way, if you're wondering where that's coming from. And then all over the Wronskian, which is 9x to the 8th. So I have then 1/9. And then integrating to retrieve u2, that will be 1/9 x. Then for your solution, remember it's y1, y2, so it's y sub c equals c1 plus c2 x to the 9th plus y1 u1 plus y2 u2. So you have to figure out y1 u1. y1 u1 is just negative x to the 10th over 90. For some reason, I think I made a mistake there. Let me pause the video, make sure. Oh yeah, so the problem, yeah. So f of x, I'm wrong. F of x is not x to the 8th. It's, oh, so that screws it up. Okay, so warning. F of x is not going to be g of x. F of x equals g of x divided by the leading variable expression. Okay, so f of x is not x to the 8th. X to the 8th is g of x. Okay, f of x is what happens when you divide everything by x. So you'd have y double prime minus 8y prime all over x equals x to the 7th. Okay, that thing then is f of x. I totally apologize. What it affects then is going to be your expressions for u1 and u2 clearly. Okay, so let me erase that and kind of start that part over. I'm sorry about that. It's the little things that count, right? So anyways, u1 prime negative y2. Where the heck is y2 at? So that's negative x to the 9th times f of x, which is turning out to be x to the 7th, all over the Wronskian, which is 9x to the 8th. So we end up with x to the 16th over x to the 8th, so negative 1/9 x to the 8th. I got to integrate both sides to get u1. u1 is negative x to the 9th over 81, or that's better. The other guy then is, what is it? y1, so y1 is 1 times f of x, which we said is now x to the 7th, over the Wronskian, 9x to the 8th. That'll be 1/9 all over x. Got to integrate both sides. So u2 is going to be factoring out the 1/9 and then integrating 1 over x. That will be ln x right there. And then you can form your solution. So the actual solution, not just yc. So the actual solution y would equal c1, the complementary part, y sub c, plus y1 u1 plus y2 u2. Okay, so let's write it. So I have c1 plus c2 x to the 9th plus y1 times u1 is just going to be the negative x to the 9th over 81. And then plus y2 u2, so x to the 9th all over 9 times ln of x. Let's make sure that's right. Yeah, that's right. Okay, let me do one more to redeem myself. Let's do number 11. X squared y double prime minus xy prime plus y equals 4x. Okay. So this time we have x squared times m times m minus 1 times x to the m minus 2 minus x times m x to the m minus 1 plus x to the m equals 4x, or 0 rather, we want the homogeneous version. Okay. You can factor out it'll be x to the m's across the board, and then you'll just be left with m times m minus 1 minus m plus 1 is 0, so m squared minus m plus 1 is 0. So you get m squared minus 2m plus 1 is 0, so m minus 1 repeated, right? M minus 1 is 0, so m equals 1 and 1, so the complementary part, y sub c, will be c1 x to the 1 plus c2 x ln x. And we can mark off our parts now, so y1 equals x, and then y2 is x ln x. So I need my Wronskian. I need f of x. Let's not screw that up again. So for f of x, I'm dividing everything by this x squared part here. So I get y double prime minus y prime all over x plus y all over x squared equals 4 all over x. 4x over x squared is 4 over x. Okay, so this is my f of x. Sorry about that. Then I get my Wronskian is x and x ln x. Differentiating, this is 1. Differentiating this other guy, first take the derivative, you have to do a product rule, right? So the derivative of x is 1 times ln x, plus leave x alone. The derivative of ln x is 1 over x, and then x times 1 over x is just 1. Okay? So the Wronskian is going to be first this times that, so x ln x plus x, and then minus that times that, minus x ln x. So very simply, it just turns into x. Okay? And then I need my little formulas that I always forget for some reason, and I don't want to obscure my y1, y2. So u1 prime is negative y2 fx, negative x ln x times fx all over w. So these x's would cancel. It looks like I'm just left with negative 4 ln x all over x. Let's make sure I got all that correct. Where's my little sheet? There we go. y2 is x ln x times f of x, which is 4 over x, all over the Wronskian, which is x. The x's cancel, so you get ln x, 4 ln x over x with a negative. Yeah. Okay, I need to integrate both sides of this thing then. I can do a u sub, I think, on the ln of x over x. So u equals ln x, and then du is 1 over x dx, and so dx is x du. So this will equal negative 4 integral of u all over x times x du. The x's cancel, and you just have the integral of u, so negative 4 u squared all over 2, which will be negative 2 and then ln x squared. Okay. What else? So I need now u2 prime. U2 prime is y1 times f of x. So y1 is just x. F of x is 4 over x, and then all over x. So I just get these cancel, so you get 4 over x. Integrating both sides, u2 must be 4 ln x. And then our solution is going to be c1x plus c2x ln x plus y1 times u1. So that will be minus 2x ln x squared, and then plus u2 times y2, which is going to be 4x ln x squared. And then you can combine these terms. So y would be c1x plus c2x ln x plus 4x ln x squared. Okay. Or 2x ln x. Oh, jeez. What is going on in my brain? 2x. Okay. And we'll check to make sure it's right, and then we'll call it a day on this video. Computer's so helpful. C1x, C2x ln x, 2x ln x squared. Looks good. Okay, we'll call it there. Call it quits there. Thank you for watching as usual, and we'll see you next time.